Welcome to Math 31. This is the second part of Lesson 9 on applications of trig functions. So I'm just going to go through the remaining two questions that you've got on your notes, and then that's going to be it for the applications. As I mentioned before, the skills you get here are pretty transferable, so you can handle a wide range of problems, hopefully. This has always been a popular one. So you got a TV camera located 1,000 meters from the site of a rocket launch. Okay, so on the ground, it's recording the event. And the rocket is launched vertically, let's say, and its elevation in meters at a certain time after liftoff is given by this formula, S is equal to 200t squared. Seems reasonable. And we want to figure out how rapidly must the camera angle be increased in order to maintain a view of the rocket 5 seconds after liftoff. So you want to make sense of this first off. Here's the illustration of it, a nice simple little one. But the camera would be right here, basically. And the camera is tracking the rocket ship. And because of the nature of the rocket's path vertically, it's going to be accelerating. It also is going to be having acceleration due to gravity affecting it downward. So we would assume that there'd be a net acceleration upwards. And but it's going to be changing. And so the problem is, or its speed is going to be changing at all times. And that means that it's actually quite a difficult task for the camera to be tracking it. You just can't sort of say, well, I think it's going to go like this. And if you want to locate it exactly, you've got to make sure that it's synced up totally on that camera, or on that rocket ship. This is where calculus comes in, because it is going to be a related rate, and lots going on. So the method that we basically use to solve one of these is we read the question first off and try to figure out what's being asked. And in this case, how rapidly must the camera angle be increased? So when you see camera angle be increased, it tells you that you actually are looking for d theta dt. So at what rate must the angle be increasing with respect to time? So always be aware of that. Now the other information we have is that this is theta there. I should indicate the angle of elevation off the ground. That's where the camera is. And this distance is fixed at 1,000 meters. As well, the vertical height, its elevation, is given by S is equal to 200t squared. So this is actually S right there. I'll just write it like that. Could call it Y if they didn't give you a variable, but I'll call it S because that's the way it's set up for it. And you need to create or choose a formula, an equation that is appropriate for this one. And it's the same as we saw earlier. In fact, it's the same as you see for a lot of problems. The tan of the angle theta will be equal to the side opposite, which is S, over the side adjacent, which is 1,000. And we're going to have to differentiate this because remember, you cannot plug in an S value and get an answer for this problem. If you plugged in an S value, all you'd get is the angle at a specific amount, but not the rate that the angle is changing. So be aware that the equations mean different things. So when we differentiate this with respect to time, and therefore getting a related rate, you might think first off that, and this is just a little bit different than I did on the previous one, you could write this as 1 over 1,000 S, and you're thinking, well, why bother? Why not multiply both sides by 1,000? And, in fact, why bother indeed? It doesn't really matter. I'm just giving you a different look at this. This might be a little bit easier. It'll save us one algebraic step later on, but nothing to worry about. You just want to make sure your algebra is flexible enough for whatever task that's in front of you. So when we do differentiate this, we will get secant squared theta times d theta dt is going to be equal to 1 over 1,000 times ds dt. And then we take stock of what we have and what we're after. This is the variable we're looking for, d theta dt. We do not have secant squared theta, just like we didn't have it for that earlier example. Nor do we have ds dt. So our next task is to get those. And secant squared theta, I'm just going to take this up to the side. So find secant squared theta at t is equal to 5 seconds. Oops. Can't use s because s is being used for position. Now, we've been here before. At t is equal to 5, if we use this formula, our position is going to be 200 times 5 squared. And if we get this value, then we can use it to actually work out what the ratio is going to be, the tan ratio. So 200 times 5 squared is 5,000. So at 5 seconds, its position is 5,000 meters. And this we can plug in so that tan theta would be equal to, at that particular instant, 5,000 over 1,000. So tan theta is equal to 5. So therefore, secant squared theta is equal to 1 plus, well, as we know, tan squared theta. So therefore, 1 plus 5 squared, which is 26. So there we go. There's our first unknown variable. So now we got secant squared theta. Now we need to get ds dt. Not a big problem because we do have a formula for s. So getting ds dt should just involve differentiating the formula for s. Now, some questions don't make you do this. They just give you the position, which is easier. This one requires a little bit more from us, but not a lot. S is equal to 200t squared. So ds dt is equal to 400t. Now, at t is equal to 5, which is what we're trying to get the rate at, you can use this Leibniz notation. That's 400 times 5. And you substitute that in, and we're going to get ds dt at t is equal to 5 is equal to 2,000. Sorry. And that would actually be meters per second if we wanted to consider that. And then we plug everything in. Secant squared theta d theta dt, I'll rewrite the equation, is equal to 1 over 1,000 ds dt. So 26 times our variable that we want, d theta dt, is equal to 1 over 1,000 times ds dt, which is 2,000. Do all the necessary cleaning up on that one. 2,000 times 1,000 is 2. And then divide by 26, and you'll get 2 over 26. So d theta dt, when you simplify, I believe I asked for an exact value, or I didn't specify, so therefore keep it as an exact value, is 1 over 13. So the camera angle must be increasing at 1 over 13 rads per second at t is equal to 5 seconds. Let's do another question. This balloon is rising at this particular amount, starting at point P. So let's get the diagram out here too. Big old balloon rising up. And an observer 100 meters from P is looking at this balloon, and the angle between his line of sight and the ground is increasing at a rate of 1 over 2 rads per second. I think originally this question was supposed to be 1 over 20 rads per second, but who cares? keep it the way it is. And we want to find the speed of the rising balloon when theta is equal to pi over 4 rads. Just so we can be clear on that, I'll put the unit in. Now, when you look at something like this, here's our theta gain, our angle of elevation or the angle of line of sight. And if you called this y, the vertical, then I think when you read the question carefully, you'll see. And by the way, pause me and go through it yourself if you'd like, if you think you're up for it. What we're looking for is the speed of the rising balloon. So we want d theta dt, or dy dt. We have d theta dt. So we set up another ratio, and it's the same as we've seen so many times. Tan of theta is equal to y over the side. Now, luckily, we have this to be 100 meters. So y over 100. So just to keep things interesting, I'm going to multiply by 100. And so again, you're thinking, why did I multiply by 100 in this case and not the previous one? It's not a big deal. Wouldn't matter if you did. I did it this time because I know that I want dy dt. So for me, it makes sense to isolate it now. But it isn't a big deal. When we differentiate at this point, we get 100 secant squared theta times d theta dt is equal to dy dt. And everything is looking just dandy. We want dy dt. We have d theta dt because that's the rad per second thing. And then secant squared theta. Okay, now this one gets interesting because instead, like the previous questions would give you a way to get secant squared theta based on the value of y, the vertical height at a certain point, and we don't have it this time. So to get secant squared theta, we don't have a linear measurement. So what we have to do is find secant squared theta at theta is equal to pi over 4. So we're given the angle instead of the side opposite. But that isn't a big deal because secant squared theta would be secant squared pi over 4. And that's equal to 1 over cos of pi over 4 all squared. So in fact, it's easier than it was using identities. The cos of pi over 4, no matter how you do it, I'll write that as 1 over root 2. And then squared. The reason I chose that is, well, actually no good reason. So 1 over 1/2 when you square it, and 1 divided by 1/2 is 2. So secant squared theta at this point is equal to 2. So easy, but you have to be aware of it. That's how we get secant squared theta. I'm going to bring up a new screen, and then let's put this one, let's finish it off. So our equation as we had it was 100 secant squared theta, got it, is equal, or d theta dt, got it, is equal to dy dt. So 100 multiplied by 2 multiplied by 1 over 2 rads per second is dy dt. So this turns into 100 meters per second is equal to dy dt. And like I said, I think the question was supposed to be, I don't know, I typoed that 1 over 20 rads per second. This balloon is really moving. But mathematically, it's fine at least. So the balloon, the elevation of the balloon is increasing at 100 meters per second at theta is equal to pi over 4 rads. And the guy looking up at this, the observer, is going to get a bit of a headache, I'd guess, but so it goes. So that's it for this. Those are the applications. And that is, in fact, the last lesson for the unit. And then the next unit will begin, well, shortly. Thank you for your time.